Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about all the fundamentals of calculus required for machine learning. Okay, so let's set up the agenda first. So we'll discuss about integration. So we'll briefly touch upon integration because it's used everywhere. You have seen earlier also in PDF, PMF. You have seen that. Okay, in PDF, sorry, in the PDFs, you have seen that it's integration. Okay, of the complete curve. Then we'll discuss about differentiation. It's all over the place. Then we'll dive deeper and understand rules of derivatives. Then we'll see limits because they are the fundamental on which the derivatives are based. So we'll understand this concept of differentiation and derivatives broadly, and then we'll see the fundamentals on which uh, differentiation or derivatives are based. So differentiation is based on limits because that's how it is defined, and also we will discuss about continuity and differentiability, whether a function is differentiable or not, and the continuity is the prerequisite for that. So we'll dive deeper into limits, continuity and differentiability. Once this is done, then we'll understand maxima minima, very important for optimization problems. Okay, for optimization point of view, because all of machine learning is optimization. So we will understand this, and then we'll understand a related concept called saddle point. Good to know. Okay, so just for completeness we'll cover this also. So that's the agenda. Let's begin. So we'll start with integration. So what is integration? We have been studying this a lot since you must have studied in 11th 12th, right? So integration, nothing. So all these are mathematical tools which will help us solve real world problems. Like it's like addition, subtraction, right? Integration is nothing but this is a mathematical tool to find area under the curve. Okay, to find area under the curve. So let's understand it quickly. So I'll give you two simple examples and then you will get the hang of it. Say for example you have one. So let me draw the coordinate axis, then it will make more sense for you. So for example I have 1 2 3, this is 3 2 1 and 1 2 3 4, like that. Okay, so we have this. So this is so we have a point here. Okay, and let's draw a triangle. So this is a triangle. Okay, let's name it ABC. Okay, so this is your origin. So this is B, this is C. So now if I have to find the area of this triangle ABC, how will you find? We know this already. So this is your area of this triangle is triangle ABC is equal to half into base into height. Simple mathematically, we know this. This is your half into base is 3 into 4. So this will be equal to like 6 units. This whole area. Okay, now again if we know derivatives will come later, right? So if we make this solve the same thing using integration, so the integration formula for basic thing like integration of okay x to the power n dx, this is given by x to the power n plus 1 divided by n plus 1 plus c. We'll ignore this constant for now. So this constant we'll ignore. So we'll only focus on this. So this is the basic formula we remember for calculus. This for integration. So if we have xn, similarly for log x, sin x, everything will have a different formula. But this is the most common format we'll discuss to understand the concept. So for xn, this is the formula. We increase the power of 1 and we divide it by the same power, increased power. It's the opposite of derivative. So integration is nothing but summation. So what do we do? So for example, if I cut this triangle into very small strips, very thin, very thin strips, very thin. Okay, and I add all those thin strips together, then I can get the area of that triangle. That's what integration. The dx is like a very thin strip, and if I know the equation of it, if I move along the equation of this line, okay. So let's change this a bit. So this is to make it simpler. So we'll make it. So this is your 1 2 3. So the equation I'm just making it simple. So the concept remains the same. Sorry. Let it be on this point 3 comma 3. Okay, and this is your triangle. is our triangle. Okay, so now what's the area of the triangle? Half into base into height, that is equal to half into 3 into 3, that is equal to 4.5, 9 by 2. Okay, and now if you say this equation of this line, right, this equation, this is nothing but y is equal to x. Here x11 y x1 y1 x2 y2, and I have taken purposefully so that it simplifies. Okay, so let's quickly understand. So if, so now we know that y, my f of x, okay, is equal to x, y is equal to f, y is equal to x, you can write like this. And if I integrate this, okay, if I integrate f of x dx, my area, I can write my area of triangle as integral f of x dx. Okay, and what will be the range of integration from here to here, from 0 to 3. So I know the equation of this curve here, sorry, it is y equal to x. I'll just put it here. So this will be equal to x dx, and what's the range? From 0 to 3. So x is changing from 0 to 3, and for y, how much is it changing? I have the equation, that is the bound of this, how x is moving, and dx are these thin strips which I'll be adding. So integration nothing but addition, so I'll be adding all through the equation of the line. That's what it means. So it gives me the area under the curve, and the curve is this here, y is equal to x, and I will just move along the curve, and I'll take thin strips, and finally I'll get the area of whatever region. So from here, this triangle is from 0 to 3. If it was 4 4, then this will be a bigger triangle. Right here the area will increase. You can just keep on increasing the area of the triangle like this, and I'll get the area of the triangle below this. Okay, so what will be the equation here? So this is equal to integration of x dx is x square by 2, and the range is from 0 to 3. So this is your upper limit minus lower limit. So 3 square is 9 by 2 minus 0 by 2. So this is equal to 4.5. Same as what we got from half base height. Okay, simple. Let's do one more example quickly so that it solidifies your concept. So we have another example. Say for example, we have a rectangle this time. So 1 2 3 4 5 6, something like this. Okay, 1 2 3 4, 1 2 3 4 5, like this. So this is your y x 0. So that's why coordinate is very important to understand. And we have, say, equation. So say for example, I have a rectangle here from here to here. So I form a quadrilateral, a rectangle, right, ABCD, like this. And the area here is this area. I want to find this area. So we know the area simply. Area for this simple thing is just length into breadth. Length into breadth is, length is here 5 minus 1 4, and the breadth is this is length, this is breadth, so 3. This is equal to 4 into 3. This is equal to 12 units, whatever is the unit. Similarly, if I want to find this area of ABCD, whatever is the quadrilateral, okay, so this will be equal to integral. So what is the area under the curve? So this is the line here, and I have to find the area. So this is the line and I have to find the area under the curve for this. So this is changing, y is changing here, and x is here, and I will take thin strips like this along the axis. I'll move along the axis, keep on taking very dx is very, dx is like delta x tend to 0, very small strips, and I'll integrate it like this, all of them, add all of them, addition, integration, nothing but addition. So what will be the equation? What is the equation of this line? This equation of this line is y is equal to 3, right? So my fx is fx dx from range 1 to 5. This is there. So this is equal to integration of 1 to 5. Fx is my fx, f of x is equal to y is equal to 3. That is my function of x, right? So this is your 3 dx. This is nothing but, what is integration of constant? That's 1. So you increase the power by 1, right? x to the power n plus 1. So I can write 1 as x to the power 0, increase the power x to the power 1 divided by 1. So finally it will become x. So this will be 3x from the range 1 to 5. So this is equal to 3 into 3 outside, x will be upper limit minus lower limit. So that is equal to 3 into 4 is equal to 12. Now I will say, what's the point? I can do it simply like this. So why am I going this way? So this is just to make you understand that that integration is nothing but your area under the curve. If you know the equation of the line or the curve, here this is a line here for 2D, that's the simplest. Here this was y equal to x, and here this is y equal to 3, that is my function of x. But what if my equation, okay, the line's equation is a bit different? Say for example, if I have a curve, for example 3, I have an equation like y is equal to x square. This is my fx. My fx is equal to y is equal to x square. This is my function. So what will be the curve look like? So y is equal to x square. This is a quadratic. So this will be a parabola, downward parabola. So this will be like this, something like this. Something like this. The drawing is not accurate, but I hope you get it. Is your y is equal to x square. Now do you have any formula for calculating the area for this? So you had this simple formula, so you said what's the need? But do we have any formula for calculating area of this thing now? If I want to calculate, say for example, these units are 1, 2, 3 like this here, and here 1, minus 1, 1, 2, 3, minus 2, minus 3 like this. And if I want to calculate the area of this between these 2 points, say from here, minus 2 to 2, okay, say, so I'll just color it off. Say from here, okay, this area from between minus 2 to 2, I want to calculate only this area. Do we have any ready-made formula for this? No, right? So that's why. So now that's the beauty of calculus. Now you have the area of the curve, and now you can just simply put the integral formula and get the area. What will be the area for this? So my fx is equal to y is equal to x square, and I want to integrate this. So my area will be equal to integral minus 2 to 2, from minus 2 to 2. I want to, this is my x-axis on which I want to integrate, and equation x squared dx. So this is equal to integral of x cube by 3 from minus 2 to 2. So this will be equal to 1 by 3, I'll keep outside. This will be x cube minus 3. So this will be 2 cube minus of minus 2 cube. So this will be equal to 1 by 3, 8 plus 8. That is equal to 16 by 3 units, whatever is units. I hope this makes sense now. This is the whole. So that's how we can calculate the area of a Gaussian also. So this is a Gaussian, right? We have done a lot of PDF. So if I know the PDF of this curve, I can integrate from whichever region to whichever region, and then I can get the area under the curve for getting the probability in this range. We know, right? From 1 standard deviation to minus 1 standard deviation, the area under the curve is 68%. So if I apply the Gaussian PDF formula, e to the power minus x minus mu whole square by 2 sigma square divided by 1 by root by 2 pi sigma. If I integrate it from plus minus 1 standard deviation, that is plus minus sigma, minus sigma to plus sigma, integrate this minus sigma to plus sigma, I will get this 68.4. Okay, and that's the whole use. Why did I say? So integration, I hope that integration is clear. If integration is clear, let's move to differentiation now. So integration is nothing but area under the curve. If you know the equation of the curve, and you can calculate the area under the curve, that's what integration is. Now let's move to differentiation. So what is differentiation? So integration is addition, then differentiation is difference. This is a difference. The formula I'll write you. So for example, dx to the power n by dx, formula I'll give you nx n minus 1. So you put the power here and reduce the power by 1. And if it's a constant, then it will be becoming 0, because constant don't change. So it is differentiation. Differentiation just measures how much a function is changing at a given point. If I want to calculate, if I have fx, okay, right, and if I want to check, okay, d by d by dx of fx at a certain point x equal to x naught, anything. So I can change that, how much is the function changing. For example, okay, I have this line, this coordinate axis, okay, and there are two lines. So this is your say for example, this is your y is equal to x, and here you have y is equal to minus x, okay, two lines. This is y equal to x, this is y equal to minus negative x, right? This is y, this is x, this is 0. So now if I ask you, what is the rate of change of y with respect to x? If x is changing by 1 unit, how much is y changing? That's what it gives. Differentiation is nothing but addition was like integration was like adding the area. Okay, so if I have this curve, I can add the area and this thing, and then I can get the curve. Now if I want to do the reverse thing, that is, if x is changing by this much, how much is this curve changing, the other one, fx? How will I find out? So it's nothing but, if you see, this is the line. Okay, if I know the slope of this line, so if I know how much is this changing at any given point, I can find out. Slope of a line is constant. Say for example, if I have a curve like this or some any other curve, so at different points the curve will be varying. In line you are seeing there's a constant slope, right? Here we know constantly. So generally a slope is defined at a point. If I have a curve like this, so at this point the slope will be different, at this point the slope will be different, at this point the slope will be different, right? A slope is the, with respect to whatever axis, that is the tan theta of that axis. This is the slope, so this is theta, so this is equal to tan theta is equal to slope, and y is equal to x means this is 45-degree line. What will be the slope of this line? If y is equal to x, then what is the slope of this line? So slope of this line is +1. If y changes by 1 unit, this will also change by, x changes by 1 unit, then y will also change by 1 unit. And similarly, this is negative, so the slope of this line will be -1. Why -1? So if you see 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Okay, I have discussed this earlier, so I'll just discuss again. So why this slope is positive slope, +1? Say if you go from 1 to 2, if x is increasing, y is also increasing here. Y will also be 1, y will also be 2. So if x is increasing, if you go towards right, then y is also increasing. But if you see for this slope, this line, why is the slope negative? Because if I'm going from towards the right, that side my x is increasing. So if I go from -2 to -1, at -2 my y was 2, at -1 my y is 1. My x is increasing because I'm moving towards right. If you move on the number line towards right, everything will be increasing, right? -2 is smaller than. So my x is increasing, but my y is decreasing. That's why the slope is negative. Okay, that's what it means. That rate of change of this variable is negative with respect to the other variable. Means if this is increasing, this is decreasing. That's what this means. I hope this is clear. What is the meaning of slope? So if this is clear, okay, let's see. So I told you, for a curve the slope this is for a line the slope is constant. But if it's a curve, say same example, if we take this one, yeah. Same example if you take here, okay. So this is a curve. Now if I want to calculate, okay, so at any point, okay, what is the derivative? So this slope is constant, yeah, so no problem. But here at this point the slope is different, at this point the slope is different, at this point the slope is different. Now if I want to calculate the formula for what is the formula for slope, so this is your tan theta, right? Tan theta will give me the slope, that is sin theta by cos theta, p by b, right? I want to know the p by b. Means if my base is changing by something, how much is my height changing, the perpendicular changing, right? That is my y change. If x is changing by how much, then y is, that's what I want to calculate. Tan theta is what? Tan theta is nothing but p by b, perpendicular by base. So perpendicular distance is your y-axis change and base distance is your x-axis change, right? If x is changing by whatever units, then what is the corresponding change in y? That's what I want to measure by slope. Right? Similarly, if I want to have a formula for tan theta, generally at a point, for line it will be a constant. So if I have only one theta, but here the theta is varying. Here it is like a line parallel to x-axis. This is 0. Here it is very steep. Okay, here it is like very small theta. Now here if you see the theta has gone very large. It is almost close to 90 degree. The slope will be like this, but it is very large, right? So I want to calculate a formula for this. How will I do? So for this there is something called how to calculate the slope at any given point. Okay, so how to calculate the slope? So now we have to do the secant tangent formula. Okay, there's a secant tangent formula. So let's do how to calculate the slope. So let's see. So let's see, we have 2 points here. Okay, we have 2 points. So say this is your x1 comma y1. This point is x1 y1 and this is your x2 comma y2. Okay, so this is your x1. So I'll just remove this. The whole axis went off so that it's clear. Only few lines are there. This is your x1, this is your x2. Okay, so then I'll rub this off. Okay, so this is your x1, this is your y1. Now if I draw for any curve, if I connect 2 points on this curve, what will this give me? So this is your nothing, this is called nothing but the secant. This is called a secant, right? And what is the slope of this secant? So this is angle theta here. Okay, so this is nothing but this is 90 degree. So what is the, if I want to have the length of the secant here, this is the length of the secant. So do I know this length and this length? If I have 2 points on this curve, if I draw a secant connecting any 2 points, and now I drop a perpendicular this side. So this point is your x1. Let me do it in, this is x1, this is x2, and the corresponding part is y1, this is here y2. So this length here will be y2 minus y1, and this length here will be x2 minus x1, right? So this is your base, this is your perpendicular, this is your theta. Tan theta is perpendicular by base. So I can calculate my tan theta. Tan theta is equal to y2 minus y1 by x2 minus x1. Simple, old school stuff. No problem till here. Rate of change of y by rate of change of x. Now, so this is your tan theta. Now what if my this thing, this x1 and x2, this is your delta x, right? So this is equal to delta y by delta x. This is a change in x, okay, or this is your delta x and this is your delta y. What if my delta x becomes, these 2 points come very close? These 2 points, x2 comes very close, this delta x tends to 0. So this will become a point at x1. If I'm coming, so x2 is very small, the delta is that x. So this x2 can be written as, let me write it. So x2 can be written as x1 plus delta x, and y2 can be written as y1 plus delta y, right? Delta y by, we'll calculate how it is, and we have the function. Okay, so we have the function also, and this is equal to f of x2, right? Or we can say this is equal to f of x1 plus delta x, your y2, and y1 is f of x1. So my tan theta is equal to delta y by delta x, that is equal to y2 minus y1 by x2 minus x1. So this is equal to what is y2? F of x1 plus delta x minus f of x1, and this is x2 minus x1 is delta x. This is nothing but x1 plus delta x minus x1. This x1 cancels off, so that's what it is. And what did we say? This is your tan theta, right? What if, okay, what if delta x tends to 0? That's what I was talking about. These 2 points will come very, very close, okay, and this secant will become a tangent because these 2 points will merge. So this secant will become a tangent, right? So this slope, whatever tan theta I have got, this will be the slope at this given point, and that's how we calculate it. So I'll just write the formula here. So now my tan theta will become, so at a given point, okay, x1 or whatever, so x, here it is the x1, right? So this is x1, okay, x1. So this is, I'll generalize it directly, okay. So you will, I'll get rid of x1 x2 here from here. So tan theta will be equal to, if I put limits to here, that meant delta x tends to 0, and I'll keep the same thing, f of x1 plus delta x minus f of x1 by delta x. So this is not your tan theta or your slope formula. I hope you remember this. Now this is what we know. This is how we get a derivative at a point. Derivative, slope, gradient, tan theta, everything is same. And as this is coming from this secant tangent formula. This is your secant, and now we move this 2 points so close together. Initially we find the tan theta for the secant, and we move this. This was because of delta x. I moved these 2 points so together. It's so close that these 2 points became very close, and this became 1 point. And that became, the secant became my tangent, and from that we got this formula. And this is your formula for, remember this is your formula for a derivative at any point. If we generalize it further, okay, so if we generalize it further, so my slope is equal to tan theta is equal to your dy by dx, that is your derivative. All these things are same, and instead of x1 I'll just remove that x1. This will be limit delta x tends to 0 f of x plus delta x, because it can be for any point. X1 was an arbitrary point, minus f of x by delta x. Okay, so this is your dy by dx derivative formula. I hope this is clear. This is clear. Let's quickly check it out, okay, if it works. We know that d by dx of x square is equal to 2x, right? We know that. Let's check it out using this formula. So what will be the so my y is equal to fx is equal to x square. So my dy by dx or tan theta will be equal to, dy by dx is nothing but rate of change of x, right? So dy by dx will be equal to limit delta x tends to 0 f of x plus delta x minus f of x by delta x. My f of x is x square, so this is limit delta x tends to 0, okay, f of x plus delta x is x square plus delta x whole square plus 2x delta x minus x square by delta x. This is nothing but a plus b whole square. I've expanded it out. Cancel this. So this is equal to limit delta x tends to 0. Take delta x common. So this will be delta x plus 2x by delta x. So again this delta x cancels off. And now apply limits. If I apply limits, this delta x will become 0, because that is 0. I'll just apply the limit, and this is, so my dy by dx okay, will become 2x, where y is equal to x square. So we have proved this with a simple formula that this is the form. Similarly, you can check out for e to the power x, log x, whatever. All this can be solved this way. I hope this makes sense. Now, if this is clear, let's move to the simple rules of derivatives. How do we take, if we have mixture of functions, so what are the rules for taking derivatives? So we'll take rules of derivatives. So I will not go through all. I will talk about all the importance which will be required for us for machine learning. Okay. So the first rule is called sum rule. Simple. Sum rule is d by dx. Everything will be d by dx of two functions fx plus gx is equal to d by dx of, okay, fx plus d by dx of gx. So now from now on I will write d by dx as d by d of f of x as f dash x. Okay, this is also a valid symbol. Okay, so instead of writing such big formulas, I'll write small one. So this is called your sum rule. Simple. Then the next rule. So my f dash, okay, this I write d by dx of product rule, fx into gx. If it is sum, this is then fx into gx. How will you do this? This will be equal to first the derivative of one, keep the other one as constant, and then take the derivative of the next and keep the first one constant. Simple. This is nothing but your product rule. Only take derivative of one at a time when we have two. Okay. Then there is a variance of this 3. If there is a quotient rule, that is numerator, denominator, fx by gx, this is called quotient, quotient, quotient rule, quotient and remainder, because this is a division, right? So you will have quotient and remainder. So what is it? So we'll do some examples also, probably you will get it. Okay, so let's see. So this is simple. This is f dash x. This is a bit tricky just to remember. So nothing, it's the same thing. Okay, it's the same thing, just a negative sign will be here, negative, and then there will be fx into g dash x, and the denominator will be there with the square. Okay, so there will be g of x whole square. So this is nothing but product rule only, but there's a negative here, and this can be also rewritten as, this is like you can write this as a product rule also. This can be right d by dx of f of x into 1 by g of x. So that can be another function, and then if you solve it, you will get the same. You will get the same formula. Say for example, let's do one example. Okay, so quickly. So for product rule, let's do for a product rule. So my function h of x is equal to x square sine x. Okay, so this is there. So my fx here is x square, and gx here is sine x, right? So my h dash x will be f dash x into g of x plus f of x as it is into g dash of x, right? So what is your x square? F dash x, this will be 2x, and this gx remains as it is. This will become sine x, plus fx will remain as it is. Fx is your x square, and g dash x, okay, derivative of sine x is cos x. So your h dash x will be this. Simple. Similarly, you can do for derivatives also, the quotient rule also. Just put the plug in the formulas, break it down fx gx. I'll talk about the more important rule. So we have this important rule that is called the chain rule. This is the backbone of back propagation when we do deep learning. So this is the derivative rule which you should know thoroughly. So this is the fourth rule. So chain rule. So what does it say? If you have a composite function, composition of functions, f of g of x, right? F of g of x. Then how do we differentiate it? This is a composite function, right? Function of a function. How do you do this? So you write f dash g of x into, so first you take f dash of g of x into g dash of x, then you independently do a derivative for g dash of x. Okay, this is used in back propagation. This is your composite function. Composite function or function of function, right? So let's do a quick example for this also. For example, your hx is, this is a bit tricky, log of x square. Okay, hx is log of x square. So we do a trick here. Let u is equal to x square. So this will become, my h of x will become log of u, right? So I can say now that this is a function of a function. Okay, so this is written as, so my h dash x can be written as, with this is your d by dx of log u, but we don't know how to differentiate this. So what we'll do is, this will be equal to d by du of log u into du by dx. We can do this, d by du of log u into du by dx. And what is my u? U is x square. I know how to differentiate u with respect to this, right? So finally it will become d by dx. This, if you see from mathematically, this will get cancelled. And this is what you will see in all of back propagation. Okay, so this is, so what is a d, or d by du of log u? This will be 1 by u, and du by dx is d by dx of x square. So this 1 by u is, you just put it x square, and d by dx of x square is 2x. X gets cancelled. This is equal to 2 by x. You can verify it easier way also. You can just put x square, so this 2 comes here, so this will be 2 log x, and log x is 1 by x. Okay, so this will become 2 by x automatically. I just gave you this bigger way to solve, to show that you can easily verify that, yeah, it is right, 2 by x. Okay, clean. All the rules are clear. So now what is differentiation? I hope you understand that. Why are we doing this? Okay, to find the slope. How to find the slope also, or the derivative. We have the formula and the rules of derivation. If that is clear, now let's go to the foundations of derivative. So my derivatives, okay, are based on limits. Okay, that's the foundation because it's defined as a limit. So let's start with limit, then we'll go to continuity, because that's the condition for a function to be differentiable. Okay, if a function is continuous, only then it will be differentiable. So then we'll understand what is continuous. So that's why I'll go from limit, continuity, then differentiability, so that the back means which function differentiable or not. So you will understand when we talk about that, when we say during linear regression, right, that mod x is not differentiable. So you will understand that theory why. So this is revision of your 11-12 stuff. Okay, so limits. So what is a limit? Let's do a quick revision. Limit, I hope you remember. What is a limit? So limit is the value of a function. Okay, the limit of function f is the value of that function as okay, so if I write that limit x tends to a f of x, this means that value of a function as x becomes very, very close to a, but not exactly, not necessarily equal to a. So I don't want it to be equal to a, but it should be very, very close to a. That's what limit means. It just be very, very as close as possible to that value a. Don't be equal to it. That's what limit means in the nearby. Okay, what is, if this is the value, then what is there? Come very close to it. That's what limit means. Okay, and it is very useful. It is used to do a lot of calculations. For example, my function f of x is there, right? F of x is defined as 1 by x. Now let's calculate the limit of it. So let's do this. So there are one-sided limits and two-sided limits. So I'll do one-sided limit now, and then I will go to the two-sided limit. So what is one-sided limit? So I will come to limit x tends to, so I want to calculate the limit of x as x tends to 0. So I will come to limit 0 from the positive side, 1 by x. So what will be the value as I come to x from the 0 side, positive side of 0? Okay, so let me show you the graph of this quickly so you will understand. So let's plot it. Plot y is equal to 1 by x. So this is a graph. I hope this is clear. Let's zoom out a bit. No, zoom in. That was fine. This was fine. Well, let's take a screenshot and I'll put it on the sheet itself. This is nothing but graph for your f of x. So if you see, if I come close to x from 0, from the positive side, this is the positive side, right? So this tends to infinity. This will go to plus infinity here. Okay, so this will be your equal to infinity, or I'll write explicitly plus infinity. And if you see, if you come to x from the negative side, this will go to the negative infinity. Okay, this will go to the negative infinity side. So if I write limit x tends to 0, it comes very close to 0 from the negative side, 1 by x, this will be equal to negative infinity. So now if I say that is limit x tends to 0 from plus 1 by x, are they equal? No, because this is plus infinity, this is minus infinity. So because of this reason, because both one-sided limits, I'm coming to the limit from, I can come to the limit from both the sides, right? Positive and negative direction. So since both the limits are not same, so we say that limit does not exist. This is the meaning of limit does not exist. So this means that limit does not exist at x equal to 0 for f of x equal to 1 by x because of the graph you saw. I hope this is clear. And now when will the limit exist? So let's take a simpler example. For example, y is equal to x square. Okay, and here let's come from 0 side. So I'll say limit x tends to 0 from positive side x square, this will be 0. And if I say limit x tends to 0 from negative side x square, this will also be 0. Both the values are same. So this implies limit exists at x equal to 0. So limit is verified at a particular point, because limit, we are moving towards a point and we want to check what will be the value of that function as it is going very, very close to that function. And do you want to see the graph of it? So let's see the graph. Plot y is equal to x square. Yeah, we have the graph. So let's see. So this is the graph. Okay, so you can see here that if I come towards 0, sorry, if I come towards 0 from the negative side, even then it will move to 0, and even if I come from the positive side towards 0, then also it will move to 0 only. So that's why limit exists. I hope this is clear. So when we say that two-sided limit exists? So here limit exists because two-sided limit, okay, means that limit x tends to a from positive side f of x is equal to, so exists, okay, if limit x tends to a negative, a from negative side f of x, and this is equal to, and this is equal to this, and this we say as limit x tends to a f of x. Okay, so this is what we say, that a limit exists at a given point, and this is one of the criteria for continuity. When we discussed all the criteria for continuity, I'll list this point down again. I hope limit is clear, right? So shall we see one more example, the controversial what I was saying. For example 3. Okay, so we have f of x is equal to mod of x, absolute value of x. So what will be the value from as at 0 from plus side? This will be mod of x is equal to x, that will be 0. And similarly limit of x tends to 0 minus mod of x equal to minus of x, that will also be 0. So both are same. This implies limit exists at x equal to 0. What will be the graph of absolute value of x? So let me get it because it's not available online. So let me get it for you. So I'll just paste it here. So this is your absolute value function. Okay. So here if you see y is equal to, this is your y is equal to mod of x. So x, if you see, whatever is the, okay, whatever is the value of x, mod of x means y will always be positive. So even if x is negative, y is positive. Even if x is positive, y is positive. So for both negative and positive x, y will always be positive. But if you see, there's a V-shaped curve here. Okay. So we'll come back to this example, but limit exists for x at x equal to 0. Limit exists because it is both. If you come from the negative side or positive side, it will be 0 only. So this is existing. Limit exists. Okay. So now if limit is clear, let's move to, because limit is the requirement for continuity also. So what's continuity? So continuity, simply put, it is that if I can, okay. So continuity of any curve at any given point is that if I can, okay, if the graph can be drawn through that point without lifting my pen, okay, this is my pen. If without lifting my pen, if I can draw the graph at that given point, then that function is continuous. Okay, so if I can draw this right without lifting my point at any point, then this is a continuous function. Some functions are like this. Say for example, this is there will be a jump. So here I have to lift my, again there will be a jump. You saw in that CDF, right? There are jumps for the probability values. Okay, so here you will have to lift the pen. So these graphs are not continuous at that points where the jump is there. There are other forms of discontinuity also, but that is one of the forms. So what are the conditions for continuity? So the thing is that we should be able to, simply put, that I should be able to draw the graph, okay, draw the graph through that point, without lifting the pen or pencil, whatever you're using, without lifting the pen. That is a simple understanding. And what are the conditions for this? There are three conditions for continuity. So what are the three conditions? First condition is that, first of all, the function should be defined at that point for a function to be continuous at a given point. So conditions for function to be continuous at given point. Okay, to check continuity at a point, any point, at any point. So first of all, the function should be f of x must be defined at point A, at x equal to A. Okay, so that is the first criteria. First of all, the function should be defined, only then we are discussing. Okay, sorry. And then the second point is limit should exist. Limit should exist means both the limits, left and right side limit, should be same. Limit should exist. This means limit limit x tends to A from positive side, f of x is equal to limit x tends to A from negative side, f of x. Both of them should be equal, only then we say limit exists. And the third point is that the value of the function at that point should be equal to the limit of the function. So what do I mean? So value must be equal to the limit at x equal to A. So like f of A, okay, f of A, that is the value of the function, this should be equal to limit x tends to A, f of A. So these are obvious, but this has to be clearly stated. So these are the three conditions for continuity. So the first term, this is the important, that limit should exist, that is defined around that. and the function should be defined at that point, so that's obvious thing. Okay, these are the reasons for continuity. So what are the examples? So for example 1, was my fx equal to 1 by x continuous at x equal to 0? No, right? Just check it out. So this, can I draw the graph without lifting my pen? No, right? So this is discontinuous here. I have to again start my graph from here. I will go till here, wherever, and then I have to lift my pen, and then I have to come here and start drawing. This is discontinuous. Similarly, this is continuous. I can go through 0, no problem. Even my where was that absolute value function? Yeah, even my absolute value function is continuous at 0. I can go to 0 and I can keep on drawing the graph, no problem. So my fx, okay, so this is not continuous. And for example, like 2, this one, okay, f of x is equal to mod x, this is continuous everywhere. And if you have functions like tan x, it is discontinuous at infinite points. You can check the graph. Okay, if you plot like, okay, let me show you. I'll just show you here itself. You can just plot tan x. What happened? How do they plot it? Yeah, you can see that it is discontinuous at many points. Here is the graph. I cannot draw the graph. If I am here, I have to come back here, there, like that. So it is discontinuous at infinite number of points. Okay. So even tan x is not continuous. So this is discontinuous at infinite points. Okay. So what is differentiability now? So continuity, the function should be continuous. So what is differentiability? Because we are coming to that only. So that's what will give me differentiation. I can calculate the derivative of a function at a given point only if it is differentiable at that point, right? And we should know whether a function is differentiable or not. How do we find that? So the first and foremost thing is that the function should be continuous there. Otherwise, if I have a jump, there is no curve, right? If my function is like this, jumping at these points, it is not continuous. How will I calculate the derivative at this point? So first of all, the function should be continuous. Only then I can take a derivative of that point. Okay. So the first thing is that the function must be continuous at given point. Okay. And the second point is that from the formula, what is your formula for derivative? Dy by dx is equal to limit delta x tends to 0, f of x plus delta x minus f of x by delta x. So this is your formula. So this limit must exist. That is it, two-sided limit. Both the sides, the limit should exist at that point. So if these two functions are conditions are met, then only we can say that a function is differentiable at a given point. First it should be continuous, and then this limit should exist. Only then this is called differentiable at a point. Now let's come back to our example. For example, f of x is equal to mod of x. We know that this is continuous. We have seen this. So first criteria is met. So f of x, so we know that this is first criteria is continuous at x equal to 0. No problem. So I am calculating at differentiability at x equal to 0. But what is the second point? The limit delta x tends to 0. This is I want to calculate the dy by dx. Okay. So what am I trying to do? I want to find f dash x at x equal to 0. So my dy by dx is equal to limit delta x tends to 0 mod of x plus delta x minus mod of x by delta x. Okay. So let's check the left and right, positive and negative side. Let's move from there. So if you go to the before 0, right? If I'm coming from here, this side. So what is the slope of this curve? This line, this side of line, we have seen this. This is plus 1, and this side the slope is minus 1. This is positive, this is plus 1, this is slope is minus 1. right? And we'll see this. So let's calculate this. So my case 1 is x is greater than 0, means I'm going from the positive side. Okay, so my limit x tends to 0 from plus side, mod of x plus delta x minus mod of x by delta x. So if this is positive, then x plus delta x is equal to x plus delta x. I can just open it up. So this is equal to limit x tends to 0 from positive side, x plus delta x minus x by delta x. So x and x gets cancelled, delta x by delta x, so this will be equal to 1, and that's what we found out also. So if I come from the positive side, my derivative is 1. And now if I want to do case 2, that is x is less than 0, then my limit x tends to 0 from negative side, mod of x plus delta x minus mod of x by delta x. So this will be equal to, so as you know, like mod of x from the negative side is minus x. Okay, if x is less than 0, then this will become minus x minus delta x, and this is minus of minus x. I've just opened up the bracket by delta x. Okay, so this minus, okay, so let me give you one more step. This is minus x minus delta x minus plus x by delta x. So this minus and plus x will get cancelled, and this will give you limit delta x tends to 0 minus delta x by delta x. These two get cancelled, and finally you will get this is equal to minus 1. Now see, compare the two values. This is 1, this is minus 1. This is minus 1. Okay, so if you come from the positive side, this is 1, and if you come from the negative side, this is 1. So the limit does not exist because both the sides are not equal. That's why we say that absolute value is not differentiable at x equal to 0, and that's the reason it is not used as a loss function. There is a hack that we use, so we have that, but that's one of the reasons that why it is not preferred for as a loss function, because it should be, loss function should be differentiable everywhere, and this is not differentiable at a very critical point, which is x equal to 0. That's often the starting point of the, okay, so my mod x is not differentiable at x equal to 0. I hope that is clear. So now let's move to the next point, that is here. Now if this is clear, we know the derivatives. Now let's move to a very important concept, maxima and minima. So you have seen this graph, right? So where is this? Y is equal to x square, yeah. So let's bring this down. This is one curve. So if you see this curve, the gradients are different at different points, and if you see at this point, what is the tangent will be? This tangent will be parallel to x-axis or the x-axis itself. So if I see at x equal to 0, my gradient is 0, sorry, dy by dx is 0, right? So, and if I see, so for this function, and similarly if I have a different graph, y equal to minus x square, say for example plot y is equal to minus x square, okay, the curve will be just reversed. So this will be the reversed parabola. Okay, this is the curve. So similarly, if you see for y equal to minus x square at 0, the curve is just reversed at y equal to minus x square. So this is your y is equal to x square. This is y is equal to minus x square. So same thing at x equal to 0, this is coming at its lowest point, this is its minima, and same function if negative, then this is coming at its maximum point, y is equal to x square. But there is one common thing, that the gradient at this point for both at x equal to 0, this has become 0, that is parallel to x-axis, nothing is changing. So the gradient at x equal to 0 is 0 for both of them. So such points where the gradient becomes 0, such points of a graph or a curve are called critical points. Okay, so these are called critical points where the derivative, so dy by dx equal to 0 at these points are called critical points. So there are similar concepts, okay, like inflection point, stationary point, okay, but dy by dx is not equal to 0. That's what we'll take. It is also there's one also case it's not defined, but we'll stick to the simple part that this is a critical point if dy by dx is equal to 0. Okay, so now how to understand whether it's a point of minima or a maxima? For that we have to take, this is here, f dash x, like first derivative. If I want to take double dash, this is your second derivative, or d square y by dx square. Okay, and that's the test we do. So for a maxima, if you see, okay, so we say that d square d, okay, so if my f double dash x is greater than 0, then this is a point of minima, and if f double dash x is less than 0, this is a point of maxima. Understand it? Okay, let's understand it. So in my maxima here, first let's see here maxima. So my gradient here, it is changing. Okay, it's changing. So from it is here till here, it is positive, 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 positive. Okay, it is here, it is incrementing, right? It is incremental. This is the gradient. So this is your positive gradient here, and then it comes positive, then it becomes 0, and then it becomes negative. Right? It is going down, down, down now. So it was going plus, 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 up, up, up. Then it becomes 0, and then it moves to negative. So it went from positive to negative. So what's the net change? It became from positive to negative. Okay, this thing, so it became positive to negative. So my net change is negative, right? It became negative. So that's why my the net change, so this is the change of derivative I'm telling, right? So the net change after that, it moved from positive to negative. So if I say y2 minus y1, that rest other part, so the net change will be negative because it's moving from positive to negative. So that's why that I'm talking about the rate of change of your gradient, rate of change of your slope, that is your first derivative. So my slope is changing from positive to negative, means the net change is negative, from plus to minus, plus 0 negative, means I'm going towards down, right? Plus 0 negative. So that's why my maxima is, my derivative, rate of change of the derivative is less than 0. That's why that is a point of maxima. And see the other way around. Here in this point, this is going down, down. It is negative gradient, right? It is negative gradient. This is negative gradient. Everything is reducing. It is negative, then it becomes 0, and then it becomes positive. Means it has hit its lowest point. It is going negative, negative, negative. It becomes 0, and then it becomes positive. So it is moving from negative gradient to positive gradient by crossing 0. So the net change is positive. So that's why that is a point of minima, and that is I'm talking about the rate of change of the gradient. So that's why if my rate of change of the second derivative, that is the rate of change of my first derivative or the gradient or the slope, if that is positive, then that point is a minima. Okay, it goes from negative, 0, positive, and here it is going from positive, 0, negative. So the net here is greater than 0 because it is going negative to positive, and here it is positive to negative, so net is 0. I hope this intuition makes clear for both of this. So now I will give you one more example, which, so a function can have both maximum and minimum. So for example, if I have a function f of x is equal to 2x cube plus 5x square. So let's do, okay, so let's do, how do we calculate point of maximum? So say if y is equal to x square, okay, so what is my y, f of x is equal to x square, then what is my f dash x equal to? This will be 2x. And what is my f double dash x? This is equal to 2, which is greater than 0. This implies this is a point of positive, means minima. Similarly, if f of x is equal to minus x square, then f dash x is equal to minus 2x, and f double dash x is equal to minus 2. This is less than 0. This implies this is a point of maxima. We have seen that I'm talking about, so if we equate it, I'm talking about x equal to 0, right? At x equal to 0. So you equate the first derivative equal to 0, so you get x equal to 0. That's the point of maxima or minima, optima. Okay, and then you find whether it is a minima or maximum point by taking the second derivative. That's the test. Okay, so first is equate it to 0. So that is your second. Okay, now let's do a third example, that where f of x is equal to cubic, maybe. Okay, 2x cube plus 5x square plus 3. So what will be my f dash x equal to? So here I'll equate it to 0 and show you. This is 6x square plus 5 2s are 10x, right? So this implies if I equate it to 0 for finding the optima, whether it's maxima or minima, so I'll get, if I take 2x common, I'll get 5x plus 3 equal to 0. This implies x equal to 0 or x equal to minus 5x plus 3, sorry, ulta, 3x plus 5, right? 2x into 3x is 6x square. So calculation mistake. So x equal to 0, I have got 2 points now. Now let's check at both the points, which is the point of maxima and minima. So let's check the derivative of f double dash x. So f double dash x will be, this was our derivative already, 6x square plus 10x. So this is your 12x plus 10, right? So at x equal to 0, my f double dash x is equal to 10, which is greater than 0. This implies this is a minima. And similarly, this is your first point, x equal to 0. Similarly, at x equal to minus 5 by 3, my f double dash x equal to 12 into minus 5 by 3. So 3 4s are 12, that is equal to minus 20. This implies less than 0. This implies this is the point of maxima. Okay, there's plus 10 also, right? There's plus 10 also. I missed that part. So this is equal to minus 20 plus 10. Still this is minus 10, which is less than 0. So this is a point of maxima. Negative means maxima. And let's see the plot of this curve quickly. What is the curve? 2x cube plus 5x square plus 3. So plot 2x cube plus 5x square plus 3. So if you see this curve, let's zoom out a bit, move this side, and not minus, just reverse, 2x cube. Let's zoom out a bit, and then you can see this curve. Okay, then zoom in a bit. This is good. Okay. So let's now look at it. So this is your, what are the points at x equal to 0? Sorry. At x equal to 0, this is your 0, right? This is your x-axis. At x equal to 0, you see this is a minima, and x equal to, what was the, sorry, these are the other points. X equal to 0, this is the minima. Yeah, x equal to 0, this is a minima, and x equal to minus 5 by 3. You see, this is a minus 5 by 3 point. This is a maxima. You see the graph? This is a maxima point. So this is your maxima. So same function, and this is your minima. Here both the points are having parallel to x-axis. Okay, this is a good example. Okay, this is clear. Let's see quickly. Okay, a multivariate. So a function in two variables, x square plus y square. So this is your example 4, I guess. So if you have two variables, how do you see this? Okay, this is your f of x comma y. So what will be my del f? We have seen vector gradient. Okay, if not, I'll put the link of that video in the description. So how do we do this? This is equal to gradient of the vector. So this will be partial derivatives, del f by del x and del f by dou f by, this is dou f by dou x and dou f by dou y. So this will be partial derivatives. Partial derivatives is nothing but it is you take the rate of change of a multivariable function with respect to only one variable at a time, keeping all the other variables constant. So for example, my f of x is like, this is x square plus y square. So now I will take the rate the derivative for this only with respect to x and keep all the variables as constant. So what will be the derivative of this with respect to x? This will become 2x, and y is constant, so this will become 0. So what will be my derivative here? 2x, and similarly this will be 2y. Okay, and I'll equate it to 0 0 because this is a vector now. So this implies x equal to 0 and y equal to 0. This is a point of some optima, maxima or minima. This just gives me whether it's a point of maxima or minima. Here both the points you saw, right? Both, it can be maxima or minima both. So this is a point of optima, we say. Some optimal point it is, point of optima. And now we have to take the second derivative, which is called a Hessian in case of this multivariate. So del square f, which is your Hessian. Okay, and what it will be? How do we calculate? This is a del square f by del x square. Here it will be del square f by del x del y. This is dou square f by dou y dou x, and this is dou square f by dou y square. Now what will this be? Hessian will be equal to, so this was what, 2x 2y. So 2x I differentiate again with respect to x, this will become 2. And now if I differentiate 2x with respect to y, this will become 0. Similarly, I have dou y by dou x here, dou f by dou y here. If I differentiate it with respect to x, this will become 0. But if I differentiate it with respect to y, dou y by dou y again for the second derivative, this will become 2. So this will be your Hessian. Okay, and if you see this, the determinant of the Hessian, this is equal to 4, which is greater than 0. This implies this is just not a, this is, the Hessian is checked for a critical point or whether it's a saddle point or not. If it is determinant is greater than 0, means this is not a saddle point, this is a point of maxima or minima. Okay, and let's see whether what it is. Okay, so let's see, let's plot it. So plot z is equal to x square plus y square. See this bowl shaped, this is a paraboloid. Okay, so for x equal to 0, y equal to 0, that is coming at the lowest point here. Okay, just rotate it and see. So this is nothing but a paraboloid. It's a parabola in 3D, and at x equal to 0 and y equal to 0, this is hitting its minimum point. So that is a point of minima. Okay, similarly, so that is your, this x equal to, this x equal to 0 and y equal to 0 is a point of minima. Also because you can see both are like greater than 0, right? This is 2 2. So since both are greater than 0, this is a point of minima. But what if, okay, what if my function is there? For example, the same function z is equal to x square by minus y square. So my Hessian will, what will my Hessian become? This will become 2. So instead of plus, that is minus, it will become 0 0 and it will be minus 2. And if we take determinant of Hessian, this will be less than 0. This will be equal to 4, but it is less than 0. This implies that it is a saddle point. What is a saddle point? Saddle point, saddle word comes from the saddle, okay, that is used to sit on a horse, okay, which is curved like this. Okay, I'll show you saddle point. So the word saddle comes from there. And what is the unique thing about it? So if you see here, I'm getting 2 positive against 1 and negative against 1. Means it is a minima against in one dimension, that is it is minima in x, and it's a point of maxima in y. And let's draw it and see. You will see this when I will rotate it, right? So let's draw this and see, and then it will be very clear to you. So if you draw x square minus y square here, so see this clearly. Okay, this is your saddle. This is like a saddle where you can, okay, you put that one side on the horse and you put both your legs on the other side, and this side it is on the horse. So one side, if you see, okay, sorry. So rotate it and see. So if you see here this point 0 0, so this is nothing but your maxima, the maximum point with respect to y. But if you rotate it with respect to x, okay, with respect to x, go back, you see this is a parabola coming down. So this is your minima with respect to, if you see from one dimension it is minima, and if you see from other direction it is your point of maxima. So that's what it is, saddle point. It is maxima with respect to one point and minima with respect to other point, and such a point is called a saddle point. It is like a saddle used to sit on a horse. You put your legs on both the sides and one side you hold. So that's the name it's coming from. Yeah, I hope saddle point is clear. So saddle point is the critical point where a function is minimum with respect to one variable. I'll just write it down for you. So where a function is min with respect to one variable and max with respect to other. Here, as you saw, it is for x it is min, and for y it is max, negative, and that's why it is a saddle point. And we saw this also here. Okay, so that is a saddle point. Say for example, in some cases so just one good to know thing. So for certain variables which are having even higher, say for example polynomials, if you have x to the power 10 or something like that, x to the power 5, so second derivative may not give you a decisive result that whether it's a point of maxima or minima. Then in such cases we go for higher order derivatives, and you can just read the Wikipedia for that, and you will get what is higher order. It has explained it very nicely. Higher order derivatives. Where is the link? Test wiki. Derivative test. Okay, it is called derivative test. So let's look at it. So if you go, there will be higher order derivative test. Yeah, this is what I'm talking about. So there is a higher order derivative test. Higher order derivative test or general derivative test is able to determine whether a function's critical points are maxima, minima, or points of inflection for a wider variety of functions than the second order derivative test. Okay, so this is, if it is not conclusive from the second derivative, then we go for higher order derivative tests. You should know this, and all the conditions are here. You no need to remember this. It's just good to know stuff, and has explained it using an example. Here the example is here. Here they have taken 6x to the power 6 plus 5. Okay, I hope that makes sense. So that is all that we had to cover. Let's quickly do a revision. What all we understood, I'll give you the broad understanding. Okay, so we understood what is integration. Integration is nothing but area under the curve of any given function, any under curve. If you know the equation, we can find the area under the curve. Integration gives you that. Differentiation is nothing but rate of change of one variable with respect to other, and the slope of that function. Okay, slope of that function gives me the gradient or slope or derivative, all are same. Okay, and for a line the slope is constant, but for a curve the slope will change at every point. That's what we saw. Then we saw the formula for finding the derivative. This is the formula. And then we discussed, because it has limits, then we understood limit. What is limit? No, we saw the rules of derivatives also. Sorry, we saw the rules of derivatives. We saw the sum rule, product rule, quotient rule, which is just a modified form of product rule, and then we saw the chain rule, which is very important, which is used for a function of function, and that is used in back propagation. We'll discuss that in detail with example when we discuss backpropagation. Okay, then we discussed limits. So one-sided limit and two-sided limit, and we saw that for a limit to exist, both the sides of the limit should be same, they should exist, and they should be equal to the same value. Then we saw continuity. Okay, that was the requirement for continuity, and we saw the conditions for continuity. There are three conditions to be satisfied, and continuity is required for a function to be, because we want to find derivatives, so the function should be continuous at that point. And continuous in literal words is that if we are able to draw a graph at that point without lifting our pen, then the function is continuous at that point. Sometimes we have jump functions, as we saw in CDFs. Okay, so you may have such functions, so those are not continuous functions. Okay, so that differentiability, that is the prerequisite, that the function should be, first of all, must be continuous, and then the second thing is the limit should exist. That's why we studied what is limit and continuity. And once we have that, we know that the function is differentiable at a point, then we can do further tests, which is the test for maxima and minima. So if the derivative of any function is equal to 0, then that is a point of a optima, maxima or minima. That is called a critical point. Okay, and we saw that x equal to 0 is a point of minima for y equal to x square, and y equal to for minus x square is the same point, is a point of maxima. And we saw that higher derivative test, the second derivative is used to determine whether it's a maxima or a minima. If the second derivative is greater than 0, then it's a minima, and if it is less than 0, then it's a maxima. I mean, this we understood the reason also, because the maxima, it's going from positive, 0, negative, so the net change is negative, and in minima it is going from negative slope to a 0 slope to a positive slope, so the net result is positive. Then we understood, we saw multivariate, and we saw one function where it has both maxima and minima. That was an example. And then we saw for multivariate, this is for multivariate where x and y both are there, and the second derivative, for that we had to calculate the Hessian. Hessian also we have discussed in another video. I'll put the link of that in the description. What is Hessian? And then we saw that if this is Hessian determinant is greater than 0, then this is not a saddle point. If it is, this is, and if it is less than 0, then that is a saddle point. And we saw what is a saddle point. This is like a horse saddle, where a function is minima with respect to one variable and maxima with respect to other. Okay, so that is all that is required for your, that is the amount of calculus required for your machine learning. I hope this, okay, this will be sufficient to understand almost most of the machine learning concepts that is required. Okay, so on that note, let's end the video. Thanks for watching this video. Have a great day ahead, and bye for now.